Hello. In this lecture we are going to discuss exponential functions and then their inverses, which are called logarithms. To begin, an exponential function takes the form as such. So let's say we have an f of x, and f of x would be 2 to the x power. Now, just for clarity's sake, even though they look similar, this function is not equivalent to the polynomial x squared. In fact, these exponential functions increase much more quickly. If we graph them side by side, we can see if we were to graph them side by side, we would see that this exponential function increases much more quickly than the polynomial y equals x squared. Now the reason for this is because the rate of change of an exponential function is proportional to the exponential itself. So the rate of change of y equals 2 to the x is proportional to 2 to the x. So just to kind of hammer in that point, let's use some of our properties of functions and look at how exactly that works. So let's say we have f of x equals 3 to the x. Well, let's say we want to look at a point shifted somewhere along that curve. So f of x plus 2, so 2 points down the line. Well, that would be 3 to the x plus 2. Alright, I mean that's straightforward enough, but let's look at what this actually is. So we can rewrite this as 3 to the x times 3 squared. So that gives us 9 times 3 to the x. So we've only shifted along our x-axis 2 units, and we're already increasing at a rate 9 times our original function. So that's why these exponentials increase so quickly. So at this point, there's a very special exponential function, and we denoted f of x equals e to the x. Now, for reasons that will be derived in calculus, this is very important, but this value e comes from the following. So e is actually equal to 1 plus 1 plus 1 over 2 times 1 plus 1 over 3 times 2 times 1 onward to infinity. And when we add up all those numbers, e comes out to about 2.718 with some more decimals, but that's usually how you see e expressed. So again, we won't go into why it's so mathematically relevant. However, bear in mind that you will see e in your future classes, and you should know where it comes from and what it means. So let's do an example problem that uses e. Let's say we have a population of bacteria, and their growth is written where the population in relation to time is equal to 1,000 times e to the 0.5 times t, where t will be our time in hours. Well, let's say that we wanted to find our population after 10 hours. All we would do is plug in 10 for t. So we can rewrite this as 1,000 e to the 5th power, and then if we evaluate this, it turns out to be 148,413. So you can see after just 10 hours of growth, we have well over 100 times the amount of bacteria that we started with, which would have been our 1,000 there. Alright, so let's look at how we solve some of these exponential functions that are just generic with x. So for example, if we had to solve 2 to the x equals 8. Well, that's straightforward enough. I mean, we can just think that through. We know that 2 to the third power is 8. So if 2 to the third power is 8, then x is simply 3. But how would we solve something like 3 to the x equals 7? So it's not clean cut there. It's going to be it's not going to be an integer. So we need some type of way to work this out algebraically. Well, that's where the inverse function of exponentials comes in. We call those logarithms. Now recall from our last lecture that to find an inverse function, we need to find something such that f of a to the x. So if we plug our exponential into the inverse function, we will get back x. So like I said, we call these logarithms, and logarithms would be written as, we abbreviate it with log base a of x. So again, that's read as log base a of x. And that turns out to be our inverse function. So let's look at the properties of it as an inverse. Well, so essentially, a to the log base a of x will return x. Also, similarly, log base a of a to the x equals x. So it works as an inverse both ways. If we plug in a log into our exponential, we get back x. If we plug an exponential into our log, we also get back x. So let's use this to solve our previous problem of 3 to the x equals 7. Alright, so let's take the log base 3 of 3 to the x equals log base 3 of 7. Well, you can see that this looks very much like this. So we're going to get x on this side, and x turns out to be log base 3 of 7. And you can plug that into a computer, or we'll learn a little later in the lecture how to get a number on your calculator. But that is an answer, and it is correct. So one thing to note about solving problems like this is we use the log base 3. Whatever the base is of our exponential, that's the logarithm we want to use. So if we had a problem such as 7 to the x equals 13, we would use log base 7 of 7 to the x equals log base 7 of 13. So this number should be the same as that number when we solve these equations. Alright, so let's look at some of our basic properties of logs. The first one that we'll look at is any log with any base b of x equal a, where a is any number, can be rewritten as b to the a equals x. Alright, so essentially all you do to move from one to the other is take everything on both sides of the equation to a base b, and you undo the log on one side, and you end up with a new exponential on the other. Fair enough. The next property is that the log of x to the n, this can be any base, is equal to n times the log of the same base of x. So all we do, if you have a logarithm, you can take an exponent and bring it out in front and multiply. Another property is that log of x times y can be rewritten as the log of x plus the log of y. Similarly, the log of x over y can be written as the log of x minus the log of y. And then two very simple concepts. The log base b of 1 is always 0, because any number to the 0 power will give you 1. So if we rewrite this using our first property, it's simply 1 equals any b to the 0 power. We know that, but this is an important thing to remember, and you don't want to switch the positions of the 1 and the 0. You can't actually take a log of 0. And our last property, which you may have already noticed, is that a log base b of b will give us 1. Alright, so these properties are going to be important when you have to manipulate logs algebraically and when you have to solve equations solving for x or y with logs in the picture. So let's just do a couple concrete examples to see how we can rearrange things using these properties. So first, let's notice that log base 2 of x to the 4th can be rewritten as 4 log base 2 of x. Those are equivalent, they're the same. Also, let's try and solve this next one, where log base 2 of x equals 4. Alright, so we can rewrite this as x equals 2 to the 4th, which is 16. So some of these log equations that you have to solve are actually very quick and straightforward if you remember your properties of logs. Alright, so let's go back and talk about e for a second. Because e is so common in mathematics, it has its own special notation for its logarithm. We call it the natural log. So the natural log would just be the log base e of x. It can also be written as ln of x. Because it's so common, most calculators have their own symbol for this logarithm, which saves you a lot of time when you're doing your homework. So let's go back to this problem where we had 3 to the x equals 7. We found that x equals log base 3 of 7, which is great. However, we need some type of computer program to actually evaluate that as it's written there. But we can use what we call the change of base formula in order to evaluate it with the calculator. So let's look at how that would work. Well, instead of using log base 3, let's use our natural log. And let's use the properties of logs to manipulate this equation. So we have 3 to the x equals 7. We take the natural log of both sides. We get that the natural log of 3 to the x equals the natural log of 7. Well, recall that we can move this x in front of our logarithm. And now we have this equation. We can divide by the natural log of 3. And we get that x is equal to the natural log of 7 over the natural log of 3. That we can put in a calculator and we can evaluate that. And this leads us to the general rule, which will be our last property, which tells us that the log base b x can be rewritten as log base a x over log base a of b. So we can rewrite any logarithm by changing the base as the ratio of this, the log of this number, the log of that number. And that can be very helpful when you're on an exam and you need an answer, or when you're doing your homework and the question calls for some numeric answer rather than the exact form.